Okay. So this will be the first example for Carnot cycle. Now a hot reservoir at 800 degrees C and a cold reservoir at 15 degrees C. So these are the two temperature limits. If let's say, for example, you are referring to a Carnot cycle consists of two isothermal processes and two isentropic process. So here, these are the two temperatures that the question has given. So this is the high temperature and this should be the lower temperature. So if you were to put it in your TS diagram, make sure convert it to Kelvin. Now calculate the thermal efficiency and the work ratio, okay, of a Carnot cycle using A as the working fluid. Now if the maximum and minimum pressures are 210 bar and 1 bar. Now, so for this, the first thing is you have to draw your Carnot cycle. Okay? Draw the property diagrams for both PV and TS for the Carnot cycle. Okay? Now, if let's say, for example, if we take A to be the working fluid, then we can assume that R, that is the specific gas constant, 0.2871, and gamma to be 1.4. Okay, the higher temperature, 800 plus 273, so that is this, plus 273, so we have 1073 K. And for lower temperature, you have 288 Kelvin. So this will be your TS diagram. Remember the two temperature line, both the isothermal process, okay, and the temperature lines, that is the high temperature and the lower temperature based on the two given temperatures, okay. Then other than two isothermal process, then you have two isentropic process. This is a Carnot cycle, okay. Remember, goes in clockwise direction. So which is your point 1? Which is the point 1? So you can just put in 4 points here. And then you can name this as point 1. Then automatically this will be 2, 3, and 4. Okay. Put in the arrows. Okay, so this will be your TS diagram for a Carnot cycle. The TS diagram for a Carnot cycle. Then for the PV diagram, pressure and volume. So the volume here is a specific volume. So these are the two temperature lines, the curve for a Carnot cycle. Okay, so this will be your 1073 Kelvin and this will be your 288 Kelvin. And then these two lines here will be your isentropic or constant entropy line. Okay, then you have this point here, these 4 points here. So in the TS diagram, this is the point 1, which is at the lower temperature, line. So this is your lower temperature line. That is your lower temperature line. So you refer to this as your lower temperature line. So you have 2 points here, either this point or this should be your point 1. Now, since you have put this here as point 1, so that is why your PV diagram, your point 1, make sure you don't put it at the wrong place. Okay, so as we can see from the TS diagram, after isothermal is isentropic. So after isothermal, you have isentropic. So this should be your point 1 here. This should be your point 1 here. So 1, this will be 2, 3, and 4. Okay. So you have this 1, 2, 3, and 4. Point 1, point 2, point 3, and point 4. Okay. So this will be your maximum pressure, that is 210 bar, and of course this 0.4 here. So you have to see, okay, which of these points here you have the maximum pressure and the minimum pressure. So this should be based on this should be your minimum pressure, that is 0.4. Okay, so that is 1 bar. So and then you have your putting the arrows all in clockwise direction, and then your volume, of course. So clockwise direction. So this is the PV diagram, and this is the TS diagram. In order for us to find heat, okay, so we have to reverse to the area of the TS diagram. For us to find the work, we can reverse to PV diagram. Okay, so what I have done here is I have drawn a table here in order for me to take down all the pressures, volume, and temperatures at each point. So altogether, there are 4 points here. So I will have 4 points. I have to know what is the pressure, volume, and temperature of each point. Then I have the point 1, 2, 3, and 4. Okay. So then I have to note, or I have to write down all the given data, that is the pressures and the temperature especially. So here, now maximum pressure is at 0.2, so that is P2, you have 210 bar. 0.4, that is your lower pressure, that is 1 bar. So you just fill it up into the tables. Okay, and then we know that, okay, both of this temperature line here, 0.1 and 0.4, is having temperature 288 Kelvin. 0.1, 0.4 having a temperature of 288 Kelvin. 0.2 and 0.3 having temperature 1073 Kelvin. So that is all the given data. Now, how are we going to find the rest of this? That means the pressure 0.1, the volume 0.1, pressure, and then the volume at 0.2, pressure at 0.3, volume at 0.3, and volume at 0.4. Okay, the most important thing is your volume here, V2 and V4 actually. But then if let's say question asks you to find the pressure, volume, and temperature at each state point, then you will have to find, definitely you have to find everything. So if let's say, for example, when you refer to this table, so you take a look at 0.2 and 0.4 here. Now, at 0.2, we have pressure, we have temperature. So in order for us to find out the volume, it's very easy by considering an ideal gas law, that is PV equals to RT. The R is given now, is assumed as 0.2871. This is a standard value for A, okay, which is kilojoules per kg/K. Okay, so you can use PV equals to RT to find out this volume here, and also based on this, also PV equals to RT to find out this volume. Okay. So stick point 1 to 2, that means we consider, let's say 1 and 2 first. Okay, 1 and 2, stick point 1, 2. Okay. Now stick point 1 to 2 here, as you can see, this is an isentropic compression process. This is an isentropic compression process. So for isentropic processes, for us to find pressure, volume, or temperature, we had a set of formulas. I hope you have watched the video or the podcast earlier, okay? Those are based on your thermal 1. So you can use this formula here. You can use this formula here to find, okay, the pressure at point 1, okay, because you got to know P2, T1, and T2. But then I am referring to 1, 2 here, okay, and from the diagram we know 1, 2 is isentropic, so that is why I use these formulas here. These formulas are only for isentropic or polytropic process. Okay, now we are looking at isentropic, so of course it's isentropic. So I have to find P1. So that is why I write here pressure ratio to temperature ratio. So if I have P1, P2, then I would have T1, T2 here. If I have P2, P1, then I should have T2 over T1. Okay? So from this, we have to find pressure P1. So P1, you can put it as subject, the subject. So our P2 is 210, okay, 210 bar. T1 and T2, we got to know 288 and 1073. Gamma for A is standard 1.4. So you can use 1.4, 1.4 here. Okay, so just substitute the values. And then you have your pressure. You have the pressure of 197.3 bar. And also one thing I have to ask you to do is to recheck. To recheck whatever I have done here. Okay, to recheck whatever I have done here. Because sometimes it might be a mistake here. Okay, so P1 is 197.3 bar. So that means 0.1 here. That is quite high. That is quite high. Okay, so you all double check. You all please double check later on. Okay, so once you have found out your pressure P1, just fill it up into the table. Okay. Then state point 3 to 4. Why am I referring to 3, 4? 3, 4, you see, there are two unknowns here. Okay, so in order to find pressure, I can use the relationship between 3, 4 process. 3 to 4 is another isentropic. So these formulas you cannot use for 2 to 3 and 4 to 1. Because 2 to 3 and 4 to 1, it is both isothermal. So these formulas here are only restricted for isentropic processes. Okay? Only restricted for isentropic processes. So if let's say I want to find pressure at point 3, so I can refer to this thing here, this process here, 3 to 4. That is isentropic. So 3 to 4 is an isentropic expansion process. So we can again use this. But then this time, pressure P3 is the subject. Pressure P3 is the subject. Okay. So put in your temperature T3 and T4 and the pressure P4. Okay, gamma. So you'll find out that your pressure P3 is 99.8 bar. Okay, please double check my work, my calculations. Yeah. Okay, please check my calculations. Then we have found out P1, so put in P1, and then also we have found out the P3, so put in your P3. Okay, so we have all the pressures now and all the temperatures. Now, if I want to find out all the volumes, it's very easy. I can use PV equals to RT, PV equals to RT, PV equals to RT, and PV equals to RT to find out volume V1, V2, V3, and V4. Okay, so state point 1. So C, state point 1 first. So you have only one unknown. Okay, so applying, this is your ideal gas law. Note for point 1 or for 1 point only. Okay, when you refers to PV equals to RT, ideal gas law, such formula, it only referring to one state point. When you refers to 1, 2, and 3, 4, that involve process. So that will be based on 2 points. You see, 3 to 4. The previous one is 1 to 2, the part A. Part B is 3 to 4. So it involves 2 points. Okay, so that's for isentropic. Both are isentropic. Now, if you refer to ideal gas law, that means this one. That means PV equals to RT, you are only referring to one state point, one row by one row. Okay, so you can apply this ideal gas law. Mass is not given. Remember, this questionnaire mass is not given. So you have to take note. That is why we use PV equals to RT. If mass is given, okay, or can be found, then we use PV equals to MRT. Okay. So volume to be the subject. So put in your R, temperature and pressure. So you can find out your volume V1, then just put in your V1 here. Okay. Then goes to the next point. Step point 2 again. Find out V2. Okay. So once you've got your V2, put it into write it down to the table. So that is 0.0147. And point 3. Again. Find out V3. Once you have found a V3, write it into the table. Okay, so that is your V3. Then point 4 to find out V4. So then you fill it up. So you have completed, okay, filling up the tables, okay, of pressure, volume, and temperature. So once you have done, then you can find your Carnot efficiency, thermal efficiency, and work ratio, and the rest, because you've got all the data here now. Now, we know that net work is equals to this net area here. Now, how to find out this net area? Remember, you have to take area under 2 to 3, okay, minus the area under 1 to 4, or 4 to 1. So 2 to 3, the area under the process path of 2 to 3 is your heat supply. And then the area under the process path of 4 to 1 is your heat rejected. So we know that net work out is heat supply minus heat rejected. So we got this. Okay. And then the change of entropy, we need to know the change of entropy also, because 2 to 3, 4 to 1 here involve change of entropy, unless 1 to 2 and 3 to 4. 1 to 2 and 3 to 4 is isentropic. Okay, isentropic, that means there is no change of entropy for 1, 2, and 3, 4. Okay, this is only for 4 to 1 and 2 to 3. And remember, the change of entropy 4 to 1 and 2 to 3 should be the same. Should be the same. Okay, so you are looking at this 4 to 1, S4 minus S1, which is also equals to S3 minus S2. So that is the change of entropy that we are looking at. Okay, so our change of entropy R is 0.2871 log base E, then our pressure maximum. Okay, based on the maximum pressure and minimum pressure, I think I have wrote something wrongly here. Now 4 and 1, between 4 and 0.1, you compare which one is the maximum pressure and which one is the minimum pressure. Okay. So you can calculate out the change of entropy is 1.517. Please double check all the workings, yeah? So once you got the change of entropy and the temperature between the two, you can find out your network, yeah? Okay, then your heat supply as well. Once you have found out the change of entropy times multiplied by TH, you get a heat supply, okay? Then you can find out the thermal efficiency or the Carnot efficiency. So network and heat supply. So you got your thermal efficiency 73.2. Please double check the working again, okay? Or you can redo the whole thing all over again on your own. I believe that these answers here are slightly different, okay? So I want you to do it on your own. Okay, I am just showing you how to do it and how to go about it. Okay, the exact answer, okay, please have to solve it. You have to solve the problem on your own. Okay. Then the gross work expansion, remember the gross work expansion is based on both the expansion work. So work 2 to 3 is given by this. Because work 2 to 3 is during isothermal. Isothermal, the work will be equal to the heat. So in order to find work 2 to 3, we have to refer to heat 2 to 3. That is given by this formula. So we can just straight away write down work 2 to 3 is this amount. Okay. And then we know that work 3 to 4 is, we are looking at isentropic process. So for an isentropic process, there is no heat flow or transfer. So therefore, the work done is equal to only the change of internal energy. So change of internal energy can be written as CVT. So you have your work done. Okay, 3 to 4. So work done 2 to 3 and 3 to 4, when you add it both, when you add both of this, you get your gross work expansion. So once you got net and gross, you can find out your work ratio. Okay, that's for the example. Thank you.